The next thing we're going to look at then is, now that we understand these things a little bit, where they are, let's look at how electrons start filling into these locations. If you remember, we just said a while ago that there are two reasons why probability increases as we approach the nucleus. The first we said was because we're looking in a much smaller space. The second has to do with how the electrons fill these energy levels, fill these subshells and orbitals. When electrons start filling subshells and orbitals, they will always start in the energy level closest to the nucleus, and they will fill their way out. And there's a set of rules in your notes to filling orbital diagrams. Let's go over those briefly. The first one says no two electrons in the same atom can have the same set of 4 quantum numbers. All right? What that's saying is, if I have a set of quantum numbers, for example, 4, 2, negative 1, m sub s is the last quantum number, and it has only two possible values. It can be plus 1/2 or negative 1/2. We call plus 1/2 spin up. Negative 1/2 is called spin down. It has to do with the way the axes spin, or the electrons actually spin. Electrons are like planets. The planet, the Earth, spins on its axis while it's revolving around the sun. These things, as they're traveling, they are spinning on their axes, right? And what we know is that in any given orbital, you can only have 2 electrons. One will be plus 1/2 spin, one will be negative 1/2 spin. Or one will be spin up, one will be spin down. They're really not spinning up and down, more spinning clockwise, counterclockwise. The reason why we can't have 2 of the same spin in there is because, again, particles that size, if they're spinning in the same direction, they would throw each other out of orbit, so to speak, and they would not stay that way. They have to spin counterbalance to counteract one another. So plus 1/2, minus 1/2. So the first rule says that no 2 electrons can have the same set. So if one electron has these quantum numbers, 4, 2, negative 1, plus 1/2, no other electron can have those set of quantum numbers. The most that they can have in common is 3 quantum numbers. They can have the same n, they can have the same L, they can have the same m sub L, but their m sub s must be different. So if another one's here and it has 4, 2, negative 1, its m sub s would have to be negative 1/2. All right, so that's rule number 1. No 2 things can have the same set of 4 quantum numbers. Called the Pauli exclusion principle. Underline that name, please. Pauli exclusion principle. It's a very important term. Number 2, each orbital can be occupied by a maximum of 2 electrons. They must have opposite spins. We already talked about 2 electrons, now we talk about opposite spins. 3, the most stable arrangement of an electron is a subshell. In a subshell is one that has the greatest number of parallel spins. That is Hund's rule. Hund's rule says that in order to start pairing up, you have to have 1 in each orbital, and you'll understand when we start getting to here in a second. So we'll come back to that one. 4, atoms in which 1 or more electron is unpaired are paramagnetic. Again, we'll come back to that. 5, in a hydrogen atom, the electron transfers depends on the principal quantum number. All right, so those other things sort of coming up, 5, 6, and 7 in your notes aren't as important as 1, 2, 3, and 4. So here's what happens. Looking at a periodic table, how do we tell how many electrons there are in an atom? What tells us, what number on the periodic table tells us the number of electrons? We've learned a lot about the periodic table and how you can look at it and tell a lot of different information. If I want to look at it and see how many electrons there are, what would I look at? Griffin?
You look at atomic number and look at its charge.
Well, not charge. We're just going to look at the atomic number. Because we're assuming we have a neutral atom. All right? In a neutral atom, we know the atomic number tells us the number of protons and the number of electrons. All right, so in your periodic table, please, everybody grab a periodic table real quick, if you have it handy in front of you. Let's take a look at hydrogen. Right, we're going to go down across here. Hydrogen has how many electrons? Its atomic number is?
1.
1, so how many electrons does it have? 1. All right, so the rule states that when electrons are filled, they start at the lowest energy levels and they fill. Now, if you'll notice, here's the order they're going to fill. These little lines represent orbitals. It's called an orbital diagram. These orbital diagrams are showing you where those electrons are. So we're sort of mapping out where the electrons are, because that's important to us when we start reacting elements together. This configuration determines everything about how they react. So the first electron in an orbital diagram would go like that. The way we represent an electron is a half arrow like that. Up means spin up, down means spin down. The rule says the first one that goes in is always spin up. So the first electron in any orbital is always spin up. Now, helium has how many electrons? 2. Its first one goes here, the second one goes here also. Spin down. All right, now, the first energy level in the 1s subshell, this orbital is full. How do I know it's full? Because there's only already two electrons, one up, one down, so no more can go there. Now, once they get filled, I have to move to the next available location. It's just like filling a bucket. As the water gets to a certain level, it has to rise up, keep filling higher levels. So we go to lithium. Lithium has 3 electrons. Spin up, spin down, its first 2. Its next one is going to go here. Which direction? Up. That would be the 3rd electron. Beryllium has 4 electrons. Where do you think the next one's going to go? 2s, down. Now, we go from there to boron. Boron's next, correct? Boron has 5 electrons. Where is the next one going to go? In the 2p subshell, because that's the next available location. All right, now here, the next one is where things start getting a little tricky. This is where Hund's rule comes in. Hund's rule, I relate to going to a little kid's birthday party. When you go to a little kid's birthday party, if you're giving out little candies or treats, the general rule says you make sure every kid gets something before you start giving out more. All right, so if you're handing out little treats, make sure every kid has had one, and then any little kid who wants more can have more, but you can't start to get more until everybody's had one. Hund's rule says in a multi-orbital subshell, this is a subshell, it has multi-orbitals, it has 3, p subshells have 3 orbitals in them, -1, 0, and 1. In a multi-orbital subshell, each orbital must have at least 1 electron before we start to pair up. Alright? So, as we go from boron to carbon, carbon has 6 electrons. 1, 2, 3, 4, 5. That's where the first 5 are going to go. The next one is going to go in the next orbital up. We say carbon has 2 unpaired electrons. We go to the next thing. What comes next? Nitrogen. Nitrogen has 7 electrons. 1, 2, 3, 4, 5, 6. The next one's going to go here. Spin up. It has 7 electrons. Now, once we have this, we have 3 unpaired electrons. Because nitrogen has 3 unpaired electrons, when you read notes, you'll hear that's called paramagnetic. And it really doesn't have much simplification to it, but you hear the words paramagnetic, diamagnetic. But that's what that means. When it says you have certain unpairs. So 3 unpaired electrons. Now, when we go to the next one, what comes after that?
Oxygen.
Oxygen. Oxygen has 8. They now start to pair up. So we come back and we start putting them in there. After that is, after oxygen is fluorine, right? Yes? Goes there. And then after that is
Neon.
neon. Goes there. Now when we're looking at the electrons, the only electrons that matter in an atom are the ones at the outermost energy level. The highest energy level that exists. In this case, the highest energy level exists, the highest N value that exists is 2. These electrons are called the valence electrons. That's a very important term, valence electrons. Valence electrons are the electrons at the highest energy level that exists for that atom. So in this case, neon has 2 in the S subshell, 6 in the P subshell in the second energy level, for a total of 8 valence electrons. We're going to find in an upcoming chapter that 8 is a magic number. Elements want to have 8 valence electrons. We're going to call that the octet rule next week when we talk about it. Alright, now, the valence electrons, the goal of all elements in their reacting is to get 8 valence electrons. They want to be like the noble gases. Remember we learned about the noble gases and their reactivity? What did we say about it? They don't. None. They don't react at all. Why do they not react? Because this is as stable as you can get. Having a filled S&P subshell in the highest energy level is as stable as you can be. That is extremely happy in their terms. They can't be any happier. They have their 8 valence electrons. That's what they want. Now, let's go back a second and look, and we'll start piecing some things together. We said that this was fluorine. All right? Now, fluorine, in order to become happy, can do 2 things. it could get rid of all 7 electrons, meaning this would be the outermost energy level, and it would be full, and it would be fine. Or it can try to gain 1 electron to fill that last subshell. Which do you think is easier to do?
Gain 1.
Gain 1. So if fluorine gains an electron, what happens to an element that gains an electron? It becomes negatively charged. What did we learn about all the halogens? They all have a charge of
-1.
-1. We now know why, because they all have the same relative configuration. They all want to gain 1 electron to be happy. That's why I knew they were all going to be -1. Let's go back a little bit more. Oxygen, we said, had 6 valence electrons. What does it want to do to be happy?
Gain 2.
Gain 2. So if it gains 2 electrons, it will be happy. All right? Let's continue on here a little bit. Let's go to the next family down, the next row down, which is sodium. I think sodium's next, right? After neon. All right, sodium has 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, what did we say sodium did when it formed an ion? What charge did it take on? Plus 1. What has to happen to become a +1 charge? You have to lose an electron. Why does sodium lose electrons? It goes back to orbital diagrams and electron configurations, how they're arranged. In order to be happy, elements want to have 8 electrons in their valence shell. Now right now, the highest energy level that has electrons in is the 3rd. So this is our valence electron. This is the outermost shell. So sodium has 2 options. It can try to pick up 7 more to fill the S&P subshell. That's what they want, to fill the S&P subshell in the outermost energy level. Or it can give away this one, making this the outermost energy level, and it's filled. What's easier to do? Lose 1. So sodium, when it forms an ion, gives that 1 away, and it has this as its outermost energy level, and it has a filled S&P subshell, or it has a noble gas configuration, we say, and it's happy. So sodium and all those tend to be +1. All right, magnesium, what do you think it wants to do?
Lose 2.
Those 2. Therefore, it's going to be +2. All right, so orbital diagrams. Now, this becomes messy. And as you see, as we start getting up here, we start getting some inconsistencies in how they fill. So using an orbital diagram, it's good for visually seeing how you start, but it's not really practical for speed or practical for understanding or looking at things. So out of this, what we're going to start looking at last here is electron configuration. And using your periodic table, you can figure out all these things by simply following a pattern that exists. Now if you look and see, we go to the 3p subshell, then we go to the 4s before we start filling the 3d. For some reason, the d subshells are slightly higher in energy than the next energy level's s subshell. When we get to the f's, we find they're actually slightly higher in energy than 2 previous s subshells. It gets complex and confusing. All right, so as you go higher and higher and higher in this orbital diagram, it gets complex. Out of that, we're going to go to now this blank periodic table, and we're going to start filling in a pattern and using some things on this.